I'm Antonio Sala, and in this video we'll continue with our study of ellipsoids. We'll discuss here intersection of an ellipsoid with a given plane or hyperplane, and also the linear transformation of an ellipsoid. If we recall, a generic ellipsoid was the body defined by this quadratic form. P was a positive semi-definite matrix. We could describe it in inverted form with Q minus 1 instead of P, and studying the properties of Q. If ellipsoids are not degenerate, those representations are equivalent. And we also discussed a third way of representing my ellipsoids just as a linear transformation of a sphere, x equal Lu. So, which are the cuts of an ellipsoid with a given line, plane or hyperplane? Imagine that we have this ellipsoid and we have a plane, say this shape, and we have this plane, well, both of them passing through the origin. Excuse for the drawing, we are just dealing with centered stuff. So this plane will be, in this case, h will be a vector, and c will be an arbitrary number that just tells me which point in the line I have. For instance, with h1, 1, I will have the 45-degree line in first and third quadrants. So, well, which is the intersection of the ellipsoid and this line? Well, it's easy. If x is hc, then I just need to replace here by hc. So here I will be c transposed h transpose, and I get the formula I wish. Of course, in the psi coordinates. As an example, if h is 1, 0, then we are just describing the horizontal axis. So if I multiply 1, 0, which is h, times p and h transposed, then we get the 1, 1 element of matrix P. So P1, 1 gives me the cut with the horizontal axis. So P1, 1 will be the P matrix of the ellipsoid, describing the cut with the horizontal axis, but of course in one dimension. Ellipsoid is just an interval, we'll see in Matlab. And P22 will be the cut with a vertical axis. Indeed, if we go to Matlab, if I have this P, then point 43 will describe me this thing, but okay, if it's one-dimensional, so point 43 will be inversely proportional to the square radius, which in 1D is just the half width of an interval. So this is why I plot the inverse square root of that thing, positive and negative. So it will give me the intersecting points with the horizontal axis, and doing the same here, we'll have the intersecting points with the vertical axis. Here we have them. P11 is inversely proportional to the square of the green points. P22 is inversely proportional to the square of the red points. Good. If we now recall the theory, we see that, okay, this is in the psi coordinates. Well, using the resulting next page, the image of this ellipsoid by exactly transformation h in the x domain can be proved to be like this. We'll do it in a minute, but the matrix inside the inverse, this one, will not be full rank, so it will be a degenerate ellipsoid, because indeed this sort of interval is a 1D object in a 2D world. It has no volume. Okay, let's go with next page, in which we will discuss the linear transformation of an ellipsoid for convenience in this inverse form. This will generalize this representation of any ellipsoid as a linear transformation of the sphere. If I am discussing a linear transformation of the sphere, then I can set Q as L transposed, and this will be the resulting ellipsoid. And what happens if we are discussing the linear transformation of an already existing ellipsoid? Well, it's easy. The original ellipsoid will be some transformation of a sphere with matrix L because any positive definite Q can have this factorization from Cholesky or eigenvalue, square root, or whatever. We explained that in a previous video. So once I have L transforming a sphere, then if I transform it with another cascade transformation multiplying that thing by C, then the overall transformation from a sphere will be matrix CL. So that's it. The matrix CL times its transposed, which is this thing, will define the resulting ellipsoid for me. And of course this thing as LL transposed was the original Q, means that new Q is CQ C transposed. So that's what we are saying here. An original Q, when the ellipsoid is transformed by a transformation matrix C, renders CQ C transposed. So for instance, if I have an ellipsoid given by Q and I wish to project it onto the horizontal axis, multiplying everything by 1, 0, so keeping only the x1 coordinate, so I have this ellipsoid. And if I multiply every vertical component by 0, then I would get this projection of the ellipsoid. Well, okay, then in that case, C1, 0, Q, C transposed will give me Q11. So Q11 gives me the projection when the ellipsoid is in inverse form, and well, we just saw that P11 gave me the intersection when the ellipsoid is in non-inverted form, kind of duality between intersection and projection. Let's go to Matlab. So imagine that I wish to project over the x1 thing, then if I have this P matrix, this will be Q, and this will be the transformation transposed. As we see here, but okay, changing C by capital T. So the P matrix of the projection will be this thing, because okay, it will be the inverse of T, Q, T transposed. Then this is it, and of course it is coincident with the Schur formula, but as the P matrices are inversely proportional to the square root of the radius or interval width in one dimension, then means that the projection size will be 1 over square root of this 0.31. And if I do the same with matrix 0, 1 when discussing the vertical axis projection, 1 over the square root of this thing will give me the projection over the vertical axis. So with this code, you can draw here the green and red circles depicting those projections, in which we basically are computing the square root of this element to give this projection, and the square root of this element to give the projection over the vertical axis, like here. So we conclude here. In this video we discussed how to compute the linear transformation of an ellipse, and we saw as an example the projection over the coordinate axis, but any arbitrary C matrix here would do. The formula was easy in inverted form, and we also compute the intersection of an ellipsoid and a hyperplane, and in this case the formula was easy in non-inverted form, and we also did use as a simple example the intersection with coordinate axis in our Matlab example. So we end the video here. Thanks for watching.